Right, welcome back. We're having a look at tutorial for this week. So there's a summary of all the information that we'll be using, so we can pick those out to help us. Alright, so each of the curves below, see if you can find stationary points, turning points, inflections, and give a bit of a graph of those. Now look, with these, I've had a look at these cubics and just double, triple checking them, as you do. And the reality is that we won't be able to find the x-intercepts. These have all got complex x-intercepts. So part of the discussion about sketching a curve is, do you just sketch parts of the curve? Well, it depends on the question. In here, you won't find anything about x-intercepts. So we're not looking at x-intercepts as such, okay? So that's just that part. It's worthwhile just making a note of that because that's important for us to recognise. All right, so let's go on with it. Okay, so for question, the question part for A is, I'm just going to drop that down a little bit. We've got a curve which we don't know anything about, and how do we find out about this curve? We go through the process of finding the derivative and assigning it to 0. So before we do that, we need to get the derivative, and we see that it's 3 out the front times 2. There's already a 3 there. 3 minus 1 is 2. 2 comes out the front times 3. X is gone, the gradient's gone on that one. So these are a cancel, and this is 6. So we get 2x squared minus 6x. So that's our derivative. So we want to find out, by doing this one, which requires us to solve, what the points are where m is 0. What are the points where m is 0? So if I take out a common factor across there, I'll be left with x and 3. 3 2 is 6x, so that should get me there. And so what we find is that x is 0, and when is this true? It's 3. So they should be our turning stationary points. Now, are they turning points? We could test the first derivative at those locations, and we could do that. But I want to just, we'll use the second derivative. We'll go and do that. This question is kind of highlighting the idea of the first derivative. And what will it look like if we have a look at the first derivative in a number of different locations. So the first couple of locations that we could look at would be 0 and 3. Clearly, they're going to be m equals 0. The question is, what's their nature? So you would have to test, so for some value like negative 1, 1, and say 4. You would have to test those values in here. And what does that tell you? Well, 2x squared minus 6 is going to be like well, it is a quadratic. But if we just check the value, so if I put 1 in, if I put minus 1 in here, it'll be positive. Minus times, so they're all positive values. So if I put minus 1 in, I get 2 plus 6, which is 8. But the important point is the derivative is behaving with a plus at minus 1, which means it's increasing. It's increasing. Okay? What I need to see is that over on this side with a 1, this changes sign. So if I put a 1 in here, it'll be 2 minus 6, which would be minus 4. Aha. So there is. See that? There's a change in sign. So that tells me that if it's going up and then down, this is a max. Okay. Now we'll check that in a minute. The other thing I want to check is 4. So 4 squared is 16. 2 16 is 32. 32 minus 24. Aha. It's a big positive again. All right. So just testing your numbers as your f derivative gives you an indication that because of the changes and that's going down, 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 and then up, 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 up. We think that's a minimum. So that's kind of the justification for the brief explanation. And the C and D, all right? So to get the points of, before we get a point of inflection, I just want to double check that with the second derivative. So the second derivative would be 4x minus 6. And I want to check those points using function notation. I'm going to check out 0 and see what's going on there. And then I'm going to check out the other one as well, which is, what do we say? 3. So in that case there, it's 4 lots of 3 minus 6. So 4 lots of 0 minus 6 is a big minus, so just exaggerate that. And 4 3 is a 12, 12 minus 6 is a big plus. So this is an upside down face, and this is a happy face. So at 0, that confirms that agrees with this y dash analysis here. That confirms that it agrees with the y dash analysis. Okay. So what we find is that oh, sorry, let's put that over there in the wrong place. Wasn't very good of me, was it? So what we find is that this is a confirmation of what we've thought earlier. Now, to find out if there's a point of inflection, what we have to do for a point of inflection is that we have to assign y double dash to 0. So that would mean solve 4x minus 6. Okay, 4x minus 6. So we just go through it. So 6 on 4, there's obviously some bits in there that match, so let's do 3 by 2 and 2 by 2, that's a 1 in disguise. So it's 1.5. There is an inflection at 1.5, and so we can find the values of all of these points by putting them back into the original function. So we can do y 0, y 3, and y 1.5. And that will give us the y coordinate of these particular parts. Alright, so the y coordinate is simply a case of putting them in and computing them. So the 0 coordinate, y0 is 5. That was too easy, wasn't it? Putting 3 in, 3 3s are 9, 3s are 27. 27 divided by 3 is 9 again, so that's 18. 3 3s are 9, 3 9s are 27, minus 27, plus 5. So minus 27, 18, 19, 20, 23, the difference is 4 there, so it'd be negative 4. Okay, so we've got coordinate points, negative 4 and 3, and 0 and 5. Alright, 3 on 2, it'll be a bit trickier, won't it? So I probably shouldn't have squished it in there, but 3 on 2 squared, it's going to be too much, I think, so I'm just going to quickly compute it. So let's do it with a calculator, because that's always handy. So we've got 3 divided by 2, and what are we doing with that? We're cubing that to the power 3. And what's that equal? Then timesing it by 2/3, and dividing that by 3. So we're back to 2.25. Now we're going to go put that in the memory, and 3 on 2 is 1.5. 3 divided by 2 1.5 squared equals times 3 negative, memory, and finally we get 5. So we get a half. So we've got a very funny little group of parts there. So we've got 0, 5, 3 minus 4, 0, 5, 3 minus 4, 0, 5, 3 minus 4, and the other parts were 1.5 gave us 1.5 gave us a half. 1.5 gave us a half. So 1.5 gave us a half. So that was our point of inflection. We worked out that 0, 5, 0, 5, because the 0 is a max. So that's our max. And 4, 3, minus 4, 3, 3 minus 4 was this one. So what we're going to do is pass that up. That'll be a concave change where it swoops down and swoops up. Go. These will head off this direction. It's sufficient that we just do that. Okay. So that's our little curve. Now you can check these, of course. Use your technology. I don't mind you doing that. We'll have you one of these things, and we'll put it all for a minute. Now, of course, this won't help you solve the question. It'll only give you a validation while you're studying. It won't make you any smarter or anything. It just gives you validation. So it's worthwhile looking into that from a validation point of view. So 1 is 2 on 3 x to the power 3 minus 3x to the power 2 plus 5 . And so there's the nice little swoops going on. So without Wolfram, we've done a pretty good job, haven't we? Without the help of Mathematica, albeit in its web-based form, ours is pretty good. So there's our maximum of 3. Our turning point's just a little bit beyond. That's up there at 5. That's exactly half of 10, so that looks right. And so on and so forth. Now we haven't named the intercepts, and as I said, these have got complex roots, so that's something that we can save up for another subject. Alright, so that's fairly straightforward. So we've got all of those things out of the way. And so we go. Just continue on doing pretty much the same thing all the way through. So x3 minus 48, so let's have a look at that one. First thing we want to do is assign that to 0, but before we can do that we need to establish what it is. And that's very short shift, isn't it? Very short shift indeed. So we need to solve this. Having 48. Undoing. So x will be equal to plus or minus the root of 16, which is plus or minus the root of 4. So at those locations, m is equal to 0. That's what we think. Okay, m is equal to 0. So if we go along and do a little bit of checking, we've got a -4 and a +4, and m is 0 there. Okay, so if we do a bit of checking, we can check, say, -5. Let's see what that looks like. We can check a 0, that'd be nice. And check a 5, that'd be okay as well. -5 and 5. So if we put 0 in, we get a negative. So that's always a nice one to try. Get a big old negative there at 0. Okay. In terms of a value. Okay. So that in terms of a value, we get a negative because we put it in here, and we get a -48. -48. Now if we put a -5 in, -5 is 25. 75 -48 is a plus. So it's a plus. And if we do the same thing for a 5, it won't matter. It'll still be a plus. So that change of sign, that's what we're looking for. That change of sign tells us that this is increasing, and then it hits this 4, -4, and then it's decreasing. So that's actually a max. Okay. The next thing is we're decreasing, and then increasing. So that's a min. That one's behaving like a min. Okay, so we validated that to that degree. All right, the next thing we want to do is substitute plus or -4 into our second derivative and just see what the concavity is, see if that agrees with what we thought. So the second derivative is going to be 6x. So we check our second derivative at -4. 6 times -4 is -24. I'm not even going to put the number. So a minus is a max. Look, there it is. It's a great validation tool. That's all you're doing. You're just checking your work and seeing how it all goes. 6 4s are 24. That's a big plus, isn't it? Big plus, so that's a smiley face. So that's your min. So you've been able to do that. Okay, so for a point of inflection, we would need y double dash to be assigned to 0. And so y double dash is in fact 6x. So we're going to be solving 6x equals 0, which is not much of an equation. Dividing by 6, you get x equals 0. So this tells us, what does it tell us exactly? That we need to do some checking. That's all. It just tells us that we need to do some checking. But really it means that the point of inflection is on the y-axis somewhere. Okay, so we'll have to have a look at that. But that makes sense because these are equal and opposite. There's some symmetry in this cubic. So the last thing I want to do is check the first values. So we've got 0 plus or minus 4. So we've got y 0, y 4, y minus 4. And these will give us our coordinates for our points. So 0 is a no-brainer. We get a -3, so that's easy. 4 is 4 4s, 16, 16 4s, 64. Okay, 4 times 48. Ooh, that's a big value. 64, 4, I think that comes out to -100. I think that comes out to -102. And at 4, it's the same thing, except that it's a positive this time. No, I'm going to have to do better than that with that one. Sorry, I'm just going to check that a bit closer. So 4 4s are 16, 4 4s are 64. 4 8s are 32. 4 4s are 16, 17, 18, 19. 192 minus 3, 195. So we've got 64 minus 195. So 64 minus 195 is minus 131. And for y minus 4, it's minus 4 all cubed, minus 48 minus 4, that'll become positive, minus 3. So we get negative 64 plus 192 this time, minus 3. So that one is 192 minus 67. Okay, so when we go and draw this now, we've got some pairs. So we're able to put some information in. We've got quite a big scale there. So we've got 4 is minus 131. So at that point there, we know we've got one of those. And at that point there, 25. We know we've got that there. Now we did compare these, didn't we? We checked that, we did a bit of checking. So minus 4 is a max. Okay, minus 4 is a max. It's swooping like this. And this one's a min, so it's swooping like this. Okay, so we've got a minus 3 as a y-intercept for this particular curve. And then what was our point of concavity, our change? So we had 0. Right, so that's all we do, we just draw them up. And we've got ourselves a picture. I'm just checking, I might need to check this. Now that's a mistake. I knew there was something that I've done. So I just have to validate these sometimes. So putting 0 in doesn't get you 0, does it? Putting 0 in gets you minus 3. Now I said it, but I didn't write it. I remember saying it probably on the video. Okay, so minus 3. Also, minus 3 happens to be, by coincidence, the place that the y-intercept occurs. So the change of concavity, or the point of inflection, is coincident with the y-intercept, which is very handy, isn't it? Very handy for us. So it'll swoop down like that, and then there's a big swooping up action. Okay, so we've drawn the bulk of the features of the curve. What remains are the returns. We don't know what the x-intercepts are, but again, we haven't been asked for them in this particular part. Okay, so there's nothing there. Now, just as easily, can check the features of the thing by doing x cubed. And these are just validations, aren't they? They're just a way of us checking and saying, well, we kind of get the idea of it, but we want to know if it actually worked the way we anticipated. Okay, 48 and -3. So we can take that away. And all that does is help us just follow through and say, well, are we in the right ballpark? Are we swooping out? The scale's quite different, but we can see the swoop there. The swoop, the maximum's happening at 4. Same here, it's just short of 5. Okay, that's hard to see there, but clearly that's just a -3 because this scale is so big. Sometimes I wish I could plot it with the scale the same, but I haven't done that yet. So, yeah, very close to what we need, and that's good enough at this point. All right, so let's keep going with it. In fact, I'm going to pause there and come back and do C, and I will see you soon.